We have a rhombus and an equilateral triangle that are interlinked. We're probably going to use the properties of both at some point. Interested in angle SQT. So I start at S, I head to Q, I head to back to T. It's the angle made in between. This one, that's what we're trying to find. Just going to focus first of all on the properties of the rhombus. So we've got one of the angles here, 110. Remember, they're all parallel lines. And okay, I'll add that on. So these two are parallel with this. Now, something to be aware of is that the opposite angles of a rhombus are the same. The reason being that if you draw the diagonal in, you can actually prove that the triangles are congruent. The top one and the bottom one, they're the same. I'm not going to do that here, but that is a little fact. And then these two add up to 220. 360 minus 220 gives 140, which we then split equally between the other two, so they're both 70. You can actually get that even more quickly by understanding co-interior angles. So if you get parallel lines like this, these two always add up to 180, which we have here. You just literally do 180 minus 110 to give 70. That's a fact worth knowing, so you can quickly use it in these situations. Let me just prove it. If I extend this, then I get corresponding angles. These two are actually equal. Essentially, I'm not going to prove that in detail either, but it's basically we've shifted this down to here. It looks exactly the same, so they must be equal. And then these two add up to 180. So it follows, because those two red angles are equal, that these two also add up to 180. It's a little semi-proof of co-interior angle theorem. So I can identify that angle as 70. Remember, we're trying to head to that red angle. Okay, this one up here is also 70. I'll write that. Now, another thing to spot is that SQ is actually a diagonal of the rhombus, and it will necessarily, again, in the same reason I talked about here, it will split the rhombus into two equal parts, and these two angles will be the same. It's a bisector, SQ is. So if we do 110 divided by 2, we get 55. Add up 55 and 70 gives 125. So if we subtract 180, we'll get this angle here, which is also 55. Okay, and actually, that's not surprising, is it? Because we have an isosceles triangle here. Okay, could have spotted that and gone with it straight away, to be fair. And then the only fact I've not used, and if you get stuck on these sorts of questions, it's always worth just thinking back. How about, is there something I've not used? I've not used the isosceles triangle here. So the two base angles are going to be the same. This is going to be 70. And so you can see this missing angle is just the difference between 70 and 55. It's going to be 15. One other approach to this question, just going to talk about, is basically understanding that these two are 70 and then realizing that this is going to be 40. And then because they're parallel, essentially we've got similar triangles, and this is also going to be 70 and 70. We can then use the fact that they're vertically opposite to give this as 70. And this is also a similar triangle down here. The reason that is useful is that then I can get 110 here. I can use my 55 here, and we add up the 110 and the 55 to give 165, and then do 180 minus that to get 15. Actually, that's how I did it, and I think it's a bit more complicated than the first method I gave, which is why I gave that one first. But it's worth seeing that there's more than one way to do this question.